Okay, so let me go back and see if there's, go back and find some exercises that we can practice with. That's not what I wanted to do. Go to the beginning. I wanted to find the exercises. Okay. Here's the chapter on determinants. So if you look at the chapter, the most important thing is this basic idea, the consequences, and the geometry of determinants, and but not the expansion property. So it's not 1.3, 1.4, just the properties required of determinants, the consequences, geometry, and that's it. The Laplace's expansion gives you those first three, that rule that we did with the 2x2 and 3x3 matrix. And we need that rule algebraically when we do eigenvectors and eigenvalues. Okay, so let us okay, so using this principle, let's look at page 478, exercise 15B. Okay, what's the determinant of this matrix? 1, 1, minus 2, 0, 0, 4, 0, 3, minus 6. You should almost be able to read, if you remember if you remember the row operation properties of bringing it to echelon form, and then the other things are upper triangular matrices, you should be able just you should just be able to write down the answer. If you look at this. So what do you think the answer is after you look at it? After you do Shruti?
Negative 18.
Excuse me?
Negative 18.
Negative 18.
Well, I remember when you were talking when we brought it back to. Oh, well, I guess you would have to bring it to echelon form.
Yeah, you have to bring it to echelon form. But how would you bring this to echelon form? And then what would be then since it's in echelon form, you can just take the product of the diagonal entries. And yeah, if you flip it, would be -1, and then you take the product of diagonal entries, so the determinant is -12. You see that? Because if I flip this, I'm going to have a 3 here and a 4 here. I have 1, 3, 4, so there'll be a minus sign from the flip. Then the product of diagonal entries will give me 12, -12. Not so. Let's see. How about 17 A? What's the determinant of this one? Using Gauss's method. What do you think?
Yeah, I mean, I have an answer, but if you want to.
So what do you think the answer is?
-3, I think.
-3, okay. So, I mean, apart from the formula, you can sort of see this is going to equal, I could do it minus and flip the two, -1, -2, -1, right? That's row one, row two, and then this one, I could pull out a -1 to cancel that -1, and I'd have 1, 1, 2, -1. And then I can do -2, row one plus row two, to give me 1, 1, 0, -3, and then it's upper triangular, so it's going to be -3. You can see the formula, the formula would be 2 times -1 minus -1 times -1 is -2 -1, which equals -3, which is the same as this. Well, here's the kind of, like, if you, does that make sense? You guys you can see how you would just, each one of these has some, like this first one here, this first one here looks like it's a 4x4, but all you have to do is -2, row one plus row two. You do that, and that's going to, -2 will kill that one, and then this one will be -2 times -2 is 4, 4 plus -4 is 0, and the product diagonal entry 1 times 0 minus 1, 5, so the determinant of this one is 0. So certain, especially sparse matrices that have a lot of zeros in them, oftentimes there's going to be something like that. Like this one, you do one row operation and get rid of the 1 and 2, there'll be an entry here, then you swap second and third rows and take the product of diagonal entries, and you can do it pretty quickly. So all of these have tricks that you can do them pretty quickly. And here's one application. For which value of K does this system, this is number 18, problem 18. For which value of K does this system have a unique solution? What does that mean to have a unique solution? That means that the matrix of entries, right? The matrix of entries of a linear system has to be non-singular, right? It's going to have a unique solution if all the variables are leading, which means that the determinant's not 0. So what we do is we would then take this and try to look at the determinant of it of x, y, and then 1, 0, and 1, K, 0, 0, and 0, 0, 1, -1. I think that would be if I've got all the things lined up. Oh no, I've got the K in the wrong place under. It's under Z, so I have 1, -2, and 1, -1, -1. Okay, so you want to know, so we have to find a determinant of this we have to find a determinant of this, then figure out for which values of K is it not 0. So you have to use a little strategy because you want to you don't. Now, if we could make this upper triangular, I only have this one and this one, right? So one thing would be it looks like that I could do minus row 4 plus row 1, right? And that would give me 1, 0, 0, 0 up here, because that would cancel this 0, 1, -2, 0, and 1, 0, K, 0, and 0, 0, 1 minus 1. And then, since this one no longer has those two, what I can do is I can add minus row 1 plus row 3 to get 1, 0, 0, 0, 0, 1, minus 2, 0, 0, 0, k 0, 0, 0, 1, minus 1. And then, okay, so obviously the first thing is k cannot be 0, right? If k is 0, you have a 0 of the determinant 0, so we wouldn't have a unique solution. So we know that k is not 0. That's important because then we could do minus 1 over k row 3 plus row 4 to get 1, 0, 0, 0, 0, 1, minus 2, 0, 0, 0, k 0, and 0, 0, 0, minus 1, right? Because that one just allows me to cancel off that 1 there. Okay, but then this is upper triangular, so therefore the determinant equals 1 times k times minus 1, which equals minus k. So it turns out that as long as k is positive, it has a unique solution.
So it can be any.
And so apparently, if this is correct, any positive k here will lead to because in some sense k is minus k is the determinant, which is weird, but
why couldn't k be negative?
it could be negative. Oh, it's not. Oh no, it could be. I meant, sorry about that. K is just not equal to 0. That's the full thing. K can be any positive or negative number, and you've got a unique value. So that's interesting because at first you think this is like a really hard problem to solve, right? How would I figure whether it has one solution or not? So I don't need, if I understand the concepts involved, I don't need to go and like solve a linear system, put it in echelon form. I can essentially do all that and find the determination from looking at the determinant of the coefficient matrix. It doesn't depend on the numbers on the right. So that's, and here's one of these sort of puzzle determinants. You know, x, y, z, x plus y, x plus z. Oh, that's pretty. Let's see.
Y plus z times y minus z.
Yeah, so there's a puzzle. There's a number 20, sort of a puzzle. It's like one of those puzzle problems. Can you think? You know, you have to see a way to show, like a proof that you're trying to find a way to show that it's 0, which probably means you need to. But you have to deal with the cases that it may be that x, y, and z are zeros or not zeros. So, but you can see there's some patterns with it. So you have to be a little careful with the oh, in fact, actually, I see. I think it's like I think I can see the trick. Yes, it's pretty straightforward. Now that you see it. Anyway, so what I will do is I'll let you puzzle over 20. as a puzzle to just think about, because this isn't so hard to see. Which the answer would be, what are the series of row operations that you want? The answer would be a series of row operations that would, and explanations that would lead for any values X, Y, and Z. So I'll let you, so everyone can have a chance. It's not that hard, but it depends on sort of insight into seeing it. But it's not that big a deal. Let's see. Let's go back and look at some more exercises. Determinants, we did that. Consequences. Well, these are sort of straightforward. I think, let's see. How about, this is on page 510. Problem 54. Find the volume of this region by using the method, not using the geometric methods, but by using the just the methods that we have developed for determinants. And assuming that these are like 1, 2, 3, 1, 2. This is 510. I mean, you can do it geometrically, but they'll check your answer. But so the question is to do it with determinants. First of all, what's the matrix you want to write down? What's the determinant you want to find? So see if you can,